right, so we're starting a new unit, the unit number 2, Introduction to Polynomial Functions. Now, we've already used the word polynomial, but what we're going to start with in this unit is to define exactly what a polynomial is. So here's the mathematical definition written right here. A polynomial function is a function of this form, and they say f at x, that's the function notation, equals. Now, this looks very complicated, but what you may notice is it's a series of terms added, or it could be subtracted, together. And you'll notice that it's a series of x terms with exponents, and in front of the x terms we can have numbers. Now, these little n's here, these are just what we call subscripts. It means here's one number, here's another number, here's another number, here's another number, etc. So we're used to seeing polynomial functions, but this is the actual definition, where the a values, a0, a1, a2, up until n, because there can be many different numbers of terms here, are all real numbers. So the coefficients in front of our x terms have to be real numbers, which is basically all the numbers that we know. And n is the number representing the number of the term, or the exponent on the x, is a whole number. Now, whole numbers are not real numbers. Real numbers are any possible numbers, decimals, pi, all of the numbers. N has to be a whole number. That means it's an integer, like a number, a whole number that we'd say whole number like 1, 8, 4, but no negatives. So all positives, or potentially 0. 0 is allowed as well. So which of the following expressions are polynomial expressions? Well, let's move that up a little bit. Okay, so to be a polynomial, it has to be a sum or difference of a bunch of terms, and the exponents have to be whole numbers, meaning 0, 1, 2, 3, 4, positive whole numbers, and the numbers in front of the coefficients, or the number in front of our x terms, have to be real numbers, which means it can be any numbers. So I'm looking at this first one. First of all, you might recognize it as a quadratic, but a quadratic is just a type of polynomial, because you notice all of our exponents are just whole numbers. There's no negatives or fractions or anything weird, and the numbers in front, the 5, the 3, and the 2, are all real numbers. So we would say that this one here, I'm going to circle all, that one is a polynomial. And then we're going to go on to the next one. Now, this one, at first you might think it is a polynomial, but notice how that square root comes right over the x as well, and a square root of an x actually has exponent 1/2, and our exponents have to be whole numbers. So this one would not be a polynomial function. Now this one, our exponents are all whole numbers, and the numbers in front, although they're odd, they are like pi and a root 5, those are real numbers. So we would say this one is a polynomial function. Now, a sine function. Now we've seen those before, I'm sure last year, when you took functions. But yes, they're a function, but they're not a polynomial function. Sine, cosine, or trig functions, not a polynomial function. Something way different. Okay, this is a simple linear function. But linear functions also have exponents that are whole numbers. 1 is a whole number, and a number in front. So yes, a linear function is a polynomial function. Now this, we've seen this type of function before as well. Now, taken individually, the numerator looks like a polynomial function, and so does the denominator. However, when we divide them, they are no longer going to be a polynomial function, because we're going to divide the x squared by this. We're also going to divide the 2 by this. This gives us a negative exponent. It's weird. It's not a polynomial. Here's a perfect, beautiful example of a polynomial function. All the exponents are positive, descending powers. Lovely polynomial. Okay, now this one, at first glance, you say, is that a polynomial? Because it doesn't have exponents. It's got brackets. But remember, if we were to multiply out those brackets, what would we get? We would get an x cubed at the beginning. We get a bunch of other things too, but they'd all have the proper whole number exponents. And then, now this one's kind of an odd one too. You might say, well, -7, that's just an integer. That's not a polynomial. But remember, there's an x there with my -7, x to the 0 power. And 0 is a whole number. So that actually is a polynomial. Okay, so we've gone through, looked at a lot of different examples. Now we're looking at a different definition. This one is the degree of the polynomial. The degree of the function, or the polynomial function, is the largest exponent of the variable in the function. So, for example, it says, for each of the above polynomials, state the degree of each one. So I'm just going to write beside the ones that I already have up here, the degree. So in this one, the ones that have check marks are polynomials. So the degree would be the highest power of x. So in the first one, my highest power of x, that's a 1, and there's nothing there, so that's a degree 2. This one isn't, so it doesn't have a degree. This one, the highest power of x would be 3, right? X cubed. Now this one, I already put the 1 in there, but we know that would be degree 1. And linear functions have degree 1. This one would have, the highest power of b would be cubed, so that would be degree 3. Now this one, we'd have to think about what would happen when we multiplied it all the way out. The highest power of x in this bracket is 1. The highest power of x here is 1, and the highest power of x here is 1. So if you multiply them all together, the highest power you're going to get is a cube. So the degree, we don't need to know exactly what it is, but we do need to know the degree would be the highest power of x, which would definitely be 3. And lastly, our friend, the little -7, that seemed to have no x at all, but in fact it had x to the 0. This would have degree 0.